Okay, we're now recording. Let's go from current slide. And before we get started, sorry I'm running a little late today. Let me go over a couple of announcements. I think you've heard at least two of them before, but one you haven't. First, but I want to keep harping. Done the student course evaluation yet? No. Okay. Please do those. Please. For you listening at home, please do your student course evaluations. Okay. We got to get our numbers up. Number one, we want to have better input for how we can improve. But a secondary issue is that we want to have good numbers when SACS comes around to do our reaccreditation. And that'll be in a few years, but they'll look back several years to see. Okay, that's one. Secondly, now this is an uncertain announcement, so I don't know exactly what's going to happen. Monday evening, I left on the Birmingham campus some paperwork that adjunct instructors who teach over there that I never see could fill out. And they were supposed to leave them with the secretary, and I was going to pick them up this afternoon. Well, after I get out of class at 3:15 and meet with that student who's going to be waiting for me, I think, and I can get a chance, I'm going to call the secretary to see if the people filled out the paperwork. If they did, I've got to go over there and pick it up. So that means normally I have office hours here on this campus from 3:15 to 5:15, but I may not today. I'll be in the office around 3:15, but just probably long enough to deal with that student, make the phone calls, make a couple copies I need to make, get my stuff together, and then I'm going to the Birmingham campus. And that takes, close to half an hour to get there, and I'm sure not going to waste another half hour driving back here. That would be 1 hour, half of my office hours would be spent driving. So already a quarter of them are going to be spent driving, so once I get over there, I'll just stay over there the rest of the afternoon. So I will be in the office sometime after 3:15 until I can work everything out, and then if the stuff's over there, I'll be going over there. If it's not over there, I'm staying here. So I may be here or I may not. The odds are at least one of those instructors came by and signed the stuff, and I've got to go take care of it now. All right, so that's today. Friday, office hours, I think I told you, normally are 7:45 to 11:45 on the Birmingham campus. Not today. See, I say on the Birmingham campus. Yeah, that's right. But not Friday because I've got an infusion Friday, and I'll be at Kirkland Clinic probably before 7 and not leave until around 4-ish or so. So not going to be on Birmingham campus or either campus at all on Friday. All right. And then just looking a little bit into the future here, first let me say this. 2 out of the 3 of you students have done your research paper. Way to go. That's good. I think I'm still missing test 1 from 2 of you, and test 2 we'll be getting pretty soon. Maybe the only other test we have, but I hope to at least cover some material in chapter 15. All right. Now, let me just explain this. I hope it's not going to happen again, but it feels like it might. Yesterday morning was the strangest thing. Overnight, no problems, never any problems, hadn't had any experience at all lately, but came into campus, no sweat, came up here, started my first class, got about halfway through it, and suddenly went into a sneezing fit. And I just sneezed and sneezed and sneezed, almost uncontrollably. And then my head drainage started happening. I mean, big time, just uncontrollable almost. It was just really bizarre. So when the class was over, I went to the restroom, and it's almost as soon as I walked out of the room, I dried up. And I went down to my office to get something to drink. Nothing. Just felt perfectly fine again. Came back to my second class, only had a 15-minute break. Came back to my second class, and before 15 minutes were over with, I was sneezing, nose running, and it was awful. I think I can't remember then or not, but it was bad. And then I had another 15-minute break. Again, went to the restroom, went down to my office, said, what's going on? As soon as I walked out of the room, dried up. It was just no more sneezing at all. Came back from my third class, 11 o'clock class, and I hadn't been in there 5 minutes, and it started again. And it was just unbelievable. I had to stop class twice and go get, because everything I had was soaking wet. I mean, it was just draining like crazy. I couldn't believe I had that much. Then, after that, I went to my office for lunch. Again, dried up. I was in there for 2 hours, office hours. Not a sneeze, no drainage, nothing. And then I had class in the afternoon here, 2 hours, not a thing. It was just, I don't know what it was. And then this morning, I've had little bits of it in both classes. And so I have a pocket full of tissues, you know, in case it starts again. Hopefully it won't, but I can feel I'm beginning to get a little bit. I had a little residual when I went down to lunch today just because I've been here for all morning long. But nothing like I had it in the room. So I don't know what it is. I just don't know what it is. All right, we were on properties of the gradient. And there are a couple of issues, and there's a little bit of a marginal note here. Sorry, I'm going to start again, I guess. Just a little bit of reminder about a dot product, okay? So, there's two really different ways you could do a dot product, both equally correct and everything. If you had two vectors, let me get my pen activated. Oh, I should have asked. Any questions on anything before we get started? Okay. Have two vectors, u and v. v dot u. Okay? Now, one definition of a dot product is merely if v is, see, what have we been dealing with? Mostly three-dimensional vectors. Let's just say v was v1, comma v2, comma v3, dotted with u1, comma u2, comma u3. Those are the components of the two vectors. And the dot product would then be a scalar, not a vector. Okay? And this would be v1 times u1 plus v2 times u2 plus v3 times u3. That's what the dot product is. The sum of the products of the corresponding components. And it's a scalar. Here's the other definition, though, of a dot product. U dot v dot u is equal to the magnitude of v multiplied by the magnitude of u times the cosine of the angle in between. I think they use theta, don't they? Yeah. Cosine of the angle in between. So again, that's a magnitude, and a number. Okay, so that gives you a scalar number as well. Two very different definitions, but they always come out being exactly the same thing. Okay? Now, another little thing. What if u was a unit vector? Okay? If u was a unit vector, then the dot product of v with u would be the magnitude of v, because that's not a unit vector. Magnitude of u would be what?
You said the magnitude of u?
Yeah. Okay, let me change one little thing here. I don't know if you recognize my thing. U is a unit vector. What's the magnitude of a unit vector? 1, exactly. So this would just be v times the cosine of theta, because the magnitude of u is always 1. No matter which way it's pointing or anything else, it's 1. Okay, now, they say here we're now in a position to draw some interesting and important conclusions about the gradient. First, suppose that the gradient of some function at some point P, some function f, and it's a scalar function, by the way, at some point P is not equal to the 0 vector. Now remember, a gradient is a vector. I usually put a line over it to remind you it's a vector. Okay? And let's say it's not the 0 vector. Okay? Nothing would work out like that. And also let U be a unit vector. U, a unit vector. Okay? Now, by the properties of the dot product, if you recall that directional derivative in the direction of U, now U is a unit vector, of the function f at the point P, if you turn back, what was it, a page or two? Yeah, one page, theorem 3, okay, or whatever it is in your book, that would be the gradient of f dot U. That would be the gradient of, and that's a vector, gradient of f dot the unit vector U. Okay. Now remembering what that is from before, gradient is a vector, not the 0 vector, so this would be the magnitude of the gradient vector times the cosine of the angle in between it and its unit vector. Okay? Now, I left off my P down here, okay? Now, if you recall, cosine theta only goes from +1 to -1 to +1. That's all. Okay? So, with that in mind, you could replace if cosine theta were -1, then minus the magnitude of f sub p would always be less than or equal to the directional derivative in the direction of u of f evaluated at p. So in other words, the cosine is always between -1 and 1. So if you put -1 on the right, +1 on the right, -1 on the left, then this thing's always going to be in between gradient of f sub p. Okay. Because if that were -1, it's going to be less than this. It will be somewhere in between these two values. So the maximum that can be with +1, minimum is that. So the gradient is always, the directional derivative is between plus or minus the gradient. That's what it's saying. Okay? Now, when this is at its maximum value, you will be at the magnitude of the gradient. When that's at its maximum value, it can be pointing in exactly the opposite direction, and then it will be at the minimum value. And in between, it can be anywhere. But it's either going to align itself with the gradient or align itself exactly opposite the gradient, and that's going to be your directional derivative. Other than that, it's going to be in between. So basically what that's telling you, in other words, the gradient vector, thing on the right, points in the direction of the maximum rate of increase of your directional derivative. Maximum rate of increase. And the opposite of the gradient vector will point in the direction of the minimum of the value that it could take on. Now, somewhere earlier, Okay. Trying to recall where that particular thing, this is in the old edition, not in the new. We don't have this anywhere in the new edition. It's a perfectly true statement, okay? For any vector v, the directional derivative in the direction of v of a function f at ab would be the gradient of that function at ab dotted with that vector v. And this was a special case if that vector happened to be a unit vector, then this comes out to be true. Now, we go back to sort of a dumb little, I'm sorry, I shouldn't say that, exercise that they did of, it's Alexa in this new edition, and it was something starting with an E in the previous edition. I don't know why they changed names, why they even give it a name, I don't know. But somebody riding a bike and looking at temperature changes as they go across country, which I guess if you're riding a bike across country, it would be important to you. But I'm trying to see where this formula shows up. This, I think, is again something in the older edition that we're really not doing anything with this edition. Okay. Not yet, anyway. I don't know if we're going to. I don't believe this is something that we address anymore. For some reason, the previous edition did. We're not. Okay. Man, it seems like oh. Okay. I think the slides got all out of order between the two editions. We've already done the slide, I think, yeah, last time, so we'll move on. Computing the directional derivatives. We even see that in the new edition. It was Theorem 3. Oh, here it is, yeah. Well, it's not quite in the same form. Okay. It's almost, but not quite. Okay. Your Theorem 3 in your book just says, if u is a unit vector, then the directional derivative in the direction of that u is given by a formula, and it's very close to this, but not quite the same. Let's blow this up. I'm trying to figure out why they made the change. This is the first time I've taught Cal 3 from this book, the new edition, and trying to wrap my head around why they've changed it. I like this better, okay? Computing the directional derivative if v is not a zero vector, is a vector but not the zero vector, and we'll assume it's not the unit vector because u is going to be the unit vector in the same direction as v. So that would be the vector v divided by its magnitude. That would give you the unit vector in the direction of v. Then the directional derivative of that unit vector, not the original vector, would be directional derivative in the direction of u of the scalar function f evaluated at point p would be 1 over the magnitude of the original vector v, not the unit vector, times the dot product of the gradient of f at p, the gradient of the scalar function f evaluated at p, dotted with that vector v. Okay? Now, you might say, why have a unit vector here and a non-unit vector here? Well, that's a good question. And maybe that's why they changed, because you notice in your book, you just have, I have to shrink it to write it, duf at p is equal to the gradient of f at p dotted with u. Oops, and use a unit vector. Okay? Now, that is exactly the same thing, because v over v over magnitude of v is the unit vector. So this is exactly the same as this, but they just left v out of it. Completely out of it, okay? So, frankly, I don't know why they even bothered with that, but they did. But that was the old edition. Your edition just has this. So I think we already did this, okay? And this is what I just did. Sorry, I was beginning here, but evidently the slide set was started at the wrong place, okay? This is what I just did from the directional derivative view from that previous definition we had at P would be the gradient of P at gradient of F at P dot U. That's exactly what we had before. And then by the definition, that's the magnitude of gradient, that's the magnitude of U, which is 1, because it's a unit vector, times the cosine of theta, which is exactly what we had. And then this is going to give you the illustration of what we were just talking about. Okay. The directional derivative in the direction of u of your scalar function f evaluated at point P, there's the point P, is going to be the magnitude of the gradient vector of f evaluated at P. There is f, the gradient of f evaluated at P. Its magnitude would be its length of that times the cosine of this angle. What does that mean? Oops, I can't write on that. Okay. Just imagine extending this line outward and then dropping a perpendicular to it. This would be that length here. I don't want to put it as a vector because it's a scalar quantity. That would be what this represents, because that's the magnitude of alpha p. That's your hypotenuse for that right triangle there. Cosine is adjacent over hypotenuse, so when you multiply the angle by the hypotenuse, you get that adjacent side. So the length of that adjacent side is exactly that. That's the directional derivative. Derivative in the direction of u of the scalar function f at point P, and that would be its magnitude. Okay? The dot product of the gradient on the unit vector, which would be the projection of that gradient onto the unit vector, the magnitude of that. Okay. Now, here we go. Now, in the old edition, again, I can't remember what her name was, but now it's Alexa. It was a different name before. And in the earlier scenario, where biker Alexa rides along a path, and that's the green line there, happens to be the path. It'll show where she's going from there. Goodness, I'm so stiff and sore. I think it's from all the sneezing yesterday. All these muscles are just hurt. Okay. I mean, literally, could hardly stop sneezing. Okay. So she's on her bike, riding along a path, as shown here. The temperature T changes at a rate that depends on the cosine of the angle in between the delta T and direction of motion. Goodness gracious. All right. Okay. Yeah, it's pretty much like it was there. So, she's biking along here on this path, and your temperature is a scalar function, not a vector function. Temperature is a scalar function. And you take the gradient of that temperature function, and it gives you this. That's the direction of the maximum increase in that temperature. She's going along like this. Let's just say she's going along like this, so that is a tangent vector there. So in that direction, the temperature changes at a rate of what its maximum would be times the cosine of the angle in between. Okay, so it's the magnitude of the gradient vector times the cosine of the angle. That would be the length of this. All right. I don't like the way they've drawn it. I don't draw well at all, but I'm going to have to shrink to write on it. But you see, if you drop a perpendicular here, that would be the rate of temperature change in that direction. Okay, sorry. It would not be this, and it's the magnitude, not a vector. So it's the magnitude, and that would be the magnitude. That length right there. I don't know why they drew the vector out that far, but it's not a vector, it's a magnitude. Now, that's if you, so the maximum of that would be if you went in the direction of the gradient. You're going at some other, so that component is going to get less, and it actually goes to 0 if this went down to here, and you were perpendicular to that, it would have 0 change. So going down in that direction, you would have no change of temperature whatsoever. Okay? Going in this way, you have a slight change in temperature. In fact, it looks like a substantial increase in temperature. There it would be 0. If you're going in a direction back this way, then the dot product of this onto a vector down this way would actually be a negative amount. So, though it can't be negative, but it would be in the other direction, but you would start increasing again. Okay. Shouldn't have even gotten to that bag of worms. Okay. Now, to me, their presentation doesn't flow too smoothly here, but they jump at this. I think this is a contour map that's going to sort of go along with Theorem 4. Here is your function. Here is your map. This is a contour map of alpha of x, y. Okay. At different levels, this would be different things. Now remember when we did, say, our shapes at the beginning, and you had the contour maps, okay? So if you had ellipsoid, sort of like a football type thing, and you took different levels, you'd have different curves. Well, this would be something more like a hyperboloid or something like that. You've got different curves. When it's equal to 40, it's there. 60, it's there. 80, it's there. 100, it's there. 120, it's there. 140, it would be there, okay? So if we just happen to pick a point on this curve there, the gradient will represent the greatest amount of increase. These graphs are at F for different values, that the function is equal to. And at this point right here where it's equal to 80, there would be the gradient there. It gives you the direction of the maximum rate of increase. Okay. If you were traveling this way or this way, you wouldn't have any change because of that gradient, because the gradient change is 0 there. Okay? If you're traveling this way, it's your maximum rate of decrease in that as you go from 80 to 60, say. Okay? This is the maximum rate of increase as you go from 80 to 100. That would be the direction to go. Okay. The gradient of P is orthogonal to the level curve through P. And that's the tangent of that level curve, so it's perpendicular to the tangent. All right. So that leads to Theorem 4, or at least illustrates, in some senses, to Theorem 4. Something I ate at lunch isn't agreeing with me too well. I'm burping too much. So the interpretation of the gradient, assume that the gradient of f at point P is not the 0 vector. We don't want to mess with that because that tells you nothing. So let's just say it's some non-zero quantity. Let u be a unit vector making angle theta with that gradient, just like the pictures we've been seeing. Then the directional derivative of u of the function f at point P is, by a definition we just did before, equal to the gradient of the magnitude of the gradient of f at P times the cosine of the angle theta in between that unit vector u, that direction of your directional derivative, and the gradient vector del f P. So del f points in the direction of maximum rate of increase of f at the point P. In other words, that del f is the maximum of this rate of increase when that cosine is equal to 1. Okay? Minus del f at P would be when the cosine of that is at 0. That points in the direction of maximum rate of decrease as you're going downhill. So let's go back to our graph that we had before. This would be increasing from 80 to 100. That's the direction you would get the maximum rate of increase. If you did the opposite of that vector, that would be the maximum rate of decrease to go from 80 to 60. It would be heading that direction. Okay. Blow up here. All right. For f, the gradient of f at P is normal to the level curve or surface of f at that point P. Okay? It's perpendicular to it, meaning that is the direction of maximum increase. Anywhere along that level curve, you don't have any change at all. That's what makes it a level curve. There is absolutely no change along that line. So the gradient gives you the maximum rate of increase. Okay. Now, we don't have this figure. This is one of the figures from the previous one we had. It's just taking a single curve there. Goodness, my eyes are having trouble focusing it. The print is really small on my screen. Yuck. I did all that and hit the wrong button. Okay, I hit the right one that time. So, if this is your level curve, whatever that shape was, whatever it was, okay? The gradient points in the direction of maximum increase. If your contour lines are smaller back here, larger up here, that's the direction you go to get maximum rate of increase in your values of that function. That's the direction you would have. All right. Goodness gracious. Okay. Now, before we do any more, let's back up and do examples 8 and 9. Okay? This is a slide from something that's coming up later. So let's do example 8 and 9. If I can get my thing to get there. All right. Okay. I think I'm okay. Here's example 8. Let f of x, function of two variables, x, y, equal this function. X to the fourth, y to the minus 2. Okay? And p is the point 2, 1. I kept thinking there was a minus sign somewhere there. I read it, but I kept thinking I had seen a minus sign. I didn't. Okay, find the unit vector. Here's the first thing it says for. And here I'm going to use u as a unit vector. Find the unit vector that points in the direction of maximum rate okay. Find the unit vector that points in the direction of the maximum rate of increase of p and determine that maximum rate. Okay. So first we want to find u in the direction of the maximum rate of increase. What do you reckon that's going to be? What direction will that be in? Say again? Right here. The gradient vector points in the direction of maximum rate of increase. So the u must be in the direction of the gradient vector. Okay? So what would be a good thing to do? Find the derivative of the gradient vector. I mean, find the gradient vector. F at point P. And that point P is 2, 1. Okay? How do you find that?
Take the partial derivative.
Yeah?
So it would just be, if you're going for the x, it would just be 4x to the third power times y to the negative 2.
Oh, yuck. Goodness gracious. Okay. Oh, my eyes are giving me fits. Okay, 4x what?
Times the y to the negative 2.
Y to the negative 2.
And then...
That's in the... Okay, you want to do it in vector notation?
Yes.
That would be the first component.
Yeah, that's
Okay.
right. And then the next one would be x to the... No, it would be...
Yeah?
Negative.
Negative.
2.
2.
X to the 4th.
Okay.
Times y.
X to the 4th times y.
Oh, yeah, to the negative 3rd.
Yeah. To the minus 3 power. Okay. you plug in that value for the xy, this is the x, there's the y, this will be, okay, let's make sure. That is the gradient. Okay, I'm sorry, not quite. Find the unit vector that points in the direction. Okay, well that's the direction. Let's figure out at that point P where that's pointing. And that would be?
So what, we now find the magnitude?
Well, the vector. That gradient vector when P is goodness gracious. I don't know why I'm writing things at the wrong. And the P is the 0.21.
Okay.
I was starting to subscript that, and I subscripted my F. I thought, why did I do that? Okay, so let's do the value there.
Okay, so that would be 32.
Just 32, right?
It is 32.
Because divided by 1 squared is 1, right?
Yeah. One quick question.
Yeah.
When it says y to the -2, and I plug in a 1,
Yeah.
it'll just be 1 still, right?
Yeah.
But when I plug in a 2, it'll just be like, I don't know how to do negative exponents. I never
Okay.
done that before, so
Oh, really?
yeah.
Okay. What that means is y to the -2 means 1 over y squared.
Okay.
The -2 means you go down with it rather than,
Oh yeah,
Yeah.
that's right. That's right.
Yeah.
I remember now. I
Yeah.
don't know why.
okay. That's the x component.
And the y component is going to be 32.
Yeah.
Yes, -32.
-32. Okay. So obviously, same dimensions, but that's not a unit vector. That's your gradient vector there. It says find the unit vector that points in that direction. So how do we get the unit vector out of that?
Find the magnitude of that? Or?
Yes. And how do we do that?
Square root of 32 squared plus -32 squared.
Which is the same as 32 squared, right?
Yeah.
Okay. Which would be 32 squared let's write it this way, the square root of 2 times 32 squared. Is that okay? Which would be the square root of 2 times the square root of 32 squared, which would be square root undoes a square, so that's 32 root 2. Right?
Yeah.
Okay? This is sort of going around your elbow to get to your nose, but I think it'll work then. So see, that's not that. This is what you're looking for. So you start with that. That's your magnitude. This is the magnitude of the gradient vector, F at P. Okay, that's what that is. Two lines there. So that's what this is. And what you do then is take alpha P, divide by its magnitude, and that would give you the unit vector in that direction would be the gradient of F at P divided by the magnitude of the gradient of F at P, which would then be 32 over 32 root 2 comma, minus 32 over 32 root 2, right? 32's go out, and basically that's the 1 over root 2, or you could say square root of 2 over 2, comma, minus square root of 2 over 2. Okay? So what would that unit vector be? And by the way, that is a unit vector. It's in the direction of this. Goodness.
I'm sorry, I'm a little lost. How did you get square root of? Oh, okay.
You could do the whole thing over that, or do each component over that. It doesn't matter. But, I mean, okay, I did skip a couple steps there. I'm trying to see which one you're missing.
Yeah, I was a little lost when he said, I thought it was 1 over square root of 32.
It is.
So that's like the alternative form of 1 over square root of 2? When you just, the answer you just wrote?
Okay. This vector is this one,
Yeah.
32 minus 32. Divide that whole vector by 32 root 2.
Yeah.
Okay. That means divide each component by that.
Okay.
Right? And that gives you your 32's cancel out as 1 over root 2 minus 1 over root 2. And if you don't like having a root 2 in the denominator, multiply numerator and denominator by root 2. This gives you a 2 down here, the root 2 here.
Okay, that's what you did. Okay.
Yeah, yeah. I did 2 steps at once. I didn't figure out where I lost you. So there's the unit vector. Well, that's the unit vector. If you think about this, okay, this would be
45 degrees.
45 degrees. That would be if those were both plus. If the second one's negative, that would be this 45. Positive in x, negative in y. That's the unit vector that goes along there. So that would be the unit vector there. So that's what it asks for. Find the unit vector that points in the direction of maximum rate of increase. That's it. Determine the maximum rate. Okay? Well, how did you get from that unit vector to that? You multiply. Okay. This is the vector in the direction of the maximum rate, so its maximum rate would be its magnitude.
Yeah.
Okay. Yeah, which you had already done. So really, you answered the second question first, and then the first question second. So it seems like it was sort of a weird way to ask the problem, but you got there, and we got both of those. Okay. Let's do example 9, and I don't think it has. No. There is a figure in the text, but it's not on the old slide set. So let's use the same slide. It won't be this figure, just like this one wasn't the figure. We're just using the white space here. Example 9. Draw a contour map and gradient vectors at various points in the plane corresponding to this function. F of xy is equal to y squared minus x squared. I can't read today. Y squared minus x squared. See, now earlier this morning, I just couldn't stop draining. And right now, for some reason, my whole head feels like it's dried to a crisp. I mean, it's extremes, you know. I feel like I can hardly breathe. There's just absolutely no moisture. I think the AC is kicked in or something. I don't know what has happened. It's strange. I don't know what to think. So draw a contour map and gradient vectors at various points in the plane corresponding to this function. Okay? Now, does that... Yeah, you have a different book. I was going to say, if you look in, I don't want to draw it, okay, is what I'm having problems with here, because this is a fairly complicated problem, but let's give it a shot. Let's use this as our coordinate system. Okay. Just ignore that. Okay. All right. So that function. Give me an x. 3. Okay. Okay. So x squared would be 9, right? Give me a y. 2. Okay. Okay. And that would be 4 minus 9 would be a negative 5. So let's see. That would be a tough way to do this. Let's do it this other way. Let's pick some values that could be. For instance, let's pick, just give me some values for f. Give me one. 5. Okay. So let's say this is equal to 5. So what x, y values would give that to you? Well, if y was root 5, which is something greater than 2, right? Then in x0, that would be a point on that contour, right? And if y was minus root 2, which would be somewhere about here, that would be on that contour, okay? Now, if x were any positive value here, for this thing to be 5, the y has to be increasing as well as the x increasing, right? Okay, because that's what the value would be when x is 0, and if x was anything other than 0, either positive or negative, y has to be, no, this one down here is not right, is it? No, it is. Yeah. It's the y value you're doing, a minus root 5, when you square it gives you 5, so that would be 5. And so anything else. So this is what, that is one contour. This is the contour when y is equal to, when f is equal to 5. Okay. Give me a color. What color would you like? Green. Okay. Give me a different value for f.
7.
Second? 7. Okay. So we'll do y squared minus x squared is equal to 7. Okay. Now, if x were 0, y would be the square root of 7, either plus or minus, right? Okay, square root of 7 is not much further up, but a little bit further up here. And then it would be like this, okay? And a little bit further down here, like that. So this would be f equals 7, f equals 7, okay? Do another one?
10.
10. I like 10 better, okay? What color you want 10 to be?
Red.
Red, okay? All right. Well, square root of 10, when x equals 0, this will be y squared minus x squared equal 10. X equals 0, this will be something greater than 3, a little bit greater than 3. So that would be about here. And these would be your hyperbolas here. That would be that. So this is f equal 10, and this is f equal 10. Okay. Now you get the general idea of where things are going there. Now that's not the whole picture, that's just part of it. Okay? in fact, let's go back to your 5. Well, let's start with the 10. What if y were 0? Then that could never equal 10, because x squared would always be positive and minus, so we could do one of y squared minus x squared equal negative 10, and that would be something here and there, and y is equal to 0. That would give you, so its curve would be something like this, something like this. These are hyperbolas, they're not parabolas. Okay? If you did, I'll continue the pattern here, and do y squared minus x squared is equal to negative 7, then it would be just like that, only here and here, here and here. Okay? And then if I did y squared minus x squared is equal to negative 5, it would be somewhere here. Okay, now there's one that we sort of left off here, and that was, what if this was equal to 0? X squared minus y squared is equal to 0. Well, some of the points on there would be 0, 0, of course. What color you want that one to be? Purple. Okay. So y squared minus x squared equals 0. One point on there would be 0, 0, right? But also 1, 1, 2, 2, 3, 3, 4, 4. So anything on your diagonal line would be that, and anything on the anti-diagonal, because if x were negative, x negative and y positive, that still is going to be the case. Okay? Or on the anti-diagonal. Okay? That would still be the case. If y were, say, negative and x were positive, but they were the same values, then that would be the case. So here's your asymptotes for those hyperbolae, and then those other hyperbolae, and they just keep filling like that. So there's the contour map. Now it says draw the gradient vectors at various points in the plane corresponding to that function. Well, what was the first one you gave me? It was, you said 3, 2.
Yeah.
So let's find the point 3, 2. 3 on x, 2 on y. It looks like it could have been here. I don't know if it was, but let's just say it was there. Okay? That's the thing. What is the contour for that? The gradient function for that? Well, it's pointing to, in a perpendicular fashion, the maximum, perpendicular from this curve toward the next curve, or whatever curve it's going to, and that would be the gradient vector. Okay? And you do that for any ones that you happen to pick. -3, how about -4, 1? Okay? Okay. This curve would be something like this, and it would be pointing in that direction. Again, perpendicular to, so those are your gradient vectors, always pointing toward, oops, I pointed it in the wrong direction, this way, because it's going from higher to lower. Wait, these are negatives, weren't they? So this one would be pointing this way, because this was a -7 here, this was a -10 here, this was a -5 there, and this is a 0 here. So it is pointing in the upward direction. I had the second one right, the first one I had backwards. That's what they mean by it. If you picked a point that was up here, then those are going in that direction because you're going to increasing them. 5, 7, 9. This was -5, -7, -9. So the usually pointing for the increasing side of things. Okay. All right. So let me erase the incorrect ones. Okay. And these over here would be pointing upward. Oops. These would be pointing upward. I have trouble drawing these things. Okay. I think that's all you had to do on that. That's all they showed. Oh, let's look at the zeros. We didn't do that. 0 pointing positive. Again, it has to be perpendicular to the curve. The positive numbers are that way, and the positive numbers are this way. Over here, the positive numbers are this way, and positive numbers that way. Okay. Yeah. Okay. So these are the positive numbers going that way, negative numbers that way, so they have to point in, positive numbers point out the y-axis. All right. Let's go to example 10. That one we do have a graph for. Let's see if we can zoom in on here and make any sense out of it. Okay. The altitude of a mountain at xy is f of xy is equal to 2500 plus 100x plus y squared e to the minus 0.3 y squared. What nice little function that is. In order for me to write that down, I've got to shrink back again. I was hoping it was going to be on here. It's not. So here's your function. Whoops, let me get back to my dark color. Okay. F of xy is equal to 2500 plus 100 times x plus y squared e to the minus 0.3 y squared. Okay. Got it. Where x, y are in units of 100 meters. Okay. So each of those, each digit you put in there is 100 meters. Okay. All right. Find the directional derivative of f at the point p, -1, -1. Okay, let's first find the directional derivative. What would that be?
The dot product between the gradient and the...
Okay, the gradient of f at p. And p was -1, -1. Okay? So what's the gradient? Let's just do the gradient first. It's going to be a vector.
The gradient would be, I feel like we already done this before, but 100 x that's it. Yeah.
All right.
And
Let's see. Not quite. If you you were, okay, this derivative of that 0. You're absolutely right. This is this times that. Plus this times this times that. So that last one gives you nothing, but this one has this in it as well.
That's true.
So, and it wouldn't be an x because that's, you're taking a couple of things wrong there. You wouldn't have the x in it because you're taking the partial with respect to x. So that would be 100.
So it's just 100
e to the minus 0.3 y squared. Okay? That's the x one. What about the y one?
The y one is going to be 200 y e to the negative 0.3. Hold up, that's another y on there. Oh, it's there. Oh yeah,
That's not all, folks.
oh, times the.
You have a product rule here, don't you?
Oh, the exponent?
Yeah. You see, you're doing the one, yeah. Oh, wait. You may have been right. Okay. Okay. I think the best thing to do, at least in my mind, is to rewrite f of x, y. To me, this makes it easier. 2,500 plus 100 x e to the minus 0.3 y squared plus 100 y squared e to the minus 0.3 y squared. I hope I'm writing that right. Yeah. Okay. Do you agree that's...
Yeah, I agree on that.
Okay. Now, so when you take the partial with respect to x, this is the only part that had that part, and that would be exactly what you had. But when you're doing the partial with respect to y, you do... That, of course, goes to 0. You have a component here, and you have two components there.
Yeah.
So you got a product rule there. And what you started off doing, I was thinking, was this part here, right?
Yeah.
Okay, that gives you the 200y e to the that. That's the very first part of it. But now you got to do the product rule, because you did the derivative of this times that. Now you got to do this, or the 100 is outside, this times the derivative of that, right?
Yeah.
Okay. So that's what I was waiting for to get on there. Okay. So that's going to be, and I put a plus there, and I do believe it's going to wind up being a minus. So ultimately, so I think I'll change that. But remember that we changed it. Okay. So you've got the second part of this one, which will be 100y squared, right?
Yeah.
Times the root of that would be e to the minus 0.3 y squared. But then you got the chain rule, which is, and this is where the minus comes from,
Negative. It'll be, oh my gosh. I don't know. My brain's not cooperating right now.
it would be 0.6y, right?
Yes.
Right?
Yeah.
Okay. Well, 100 times negative 0.6 would be negative 60, and you had a y from this and a y squared from that, so it's negative 60y cubed. So let me get my eraser in here to make that a minus 60y cubed. Okay. Okay, but we're not done yet. Okay. So what we did, this part here was when you did derivative of this times that, right?
Okay, yeah.
And then the second part was when you did this times the derivative of this, right?
Yes.
Well, that would be 100y squared times the derivative of this is itself. Then you have the chain rule, which would give you negative 0.6y. So 100 times negative 0.6 would then give you the minus 60. And you already had a y squared, and the other y gave you a y cubed. Okay? So that's this part. But you haven't taken the derivative of this with respect to y. Well, that would be plus, now derivative of this one with respect to y. Well, the 100x just acts like a constant.
Yeah.
So we'll just write that down. We're going to come back and multiply something by either. And then you have e to the minus 0.3 y squared, right? But then you do the chain rule of that with respect to y, which is again a negative 0.6 y. So this will be a negative 60, right? xy. The x was from the 100x and the y from the chain rule of the other. That's all your y component. Whoa. All right. Now let's evaluate that at -1, -1. It's going to get a lot better. Okay. So at -1, -1, this will be 100 e to the negative 0.3, right? Because y is -1, y squared would be +1, so that would just be that. The second part, the y component, is going to be, put a -1 in there, that would be -200 e to the minus 0.3 minus, okay, would have been a minus 60, but then you're doing y cubed, which will be a -1, so that's going to be a plus 60 e to the minus 0.3. And this stays a minus 60 because you're doing xy. X is -1, y is -1. So that's minus 60 e to the minus 0.3. Well, guess what? Those two add to 0. There's your vector. I told you it'd get a lot nicer. Okay? That is the gradient vector. I love this problem, don't you?
Yeah.
Okay. The directional derivative of f at that in the direction of the unit vector u make, oh, wait a minute, I didn't read the whole problem. Why didn't I read the whole problem? Yeah. Find the directional derivative of f at that point. That's where I stopped. I didn't read in the direction of the unit vector u making an angle of theta equal pi fourths with the gradient. Okay? All right.
Well, we still would have had to take this round anyway.
Yeah, we had to do this anyway, and we got that done. Okay? And what we have to do is making an angle of theta pi fourths. Well, you see if you turn back to the, well, you don't have it.
No.
Okay. If we go back to this, the directional derivative in a unit vector, that function is the gradient of f. Okay. We haven't done the magnitude of it. Okay. But times the cosine of the theta. Well, theta is pi fourths, so that would be square root of 2 over 2. Okay. So what we have to do now, we've gotten that right. We got to find its magnitude. Okay. So Oh, wait. I forgot about this thing, x being in units of 100 meters. No, I think we're okay. All right. So let's actually calculate. Do you have a calculator with you?
Yeah.
Okay. It'll be a lot easier to go on and do this evaluation. Hundred times e to the minus 0.3.
So 100 times e to the minus
Negative 0.3.
Okay. And plus or
What's that?
we're just doing the magnitude, right?
Yeah, doing this one.
Alright. Shoot. I'm gonna have to start it back. I'm sorry.
That's that.
I was typing it wrong.
Okay.
And I have 165.65.
I don't think it can possibly be greater than 100. Because e to the minus 3 is less than 1. E to the minus 0.3, I'm sorry.
Yeah, that's what I put in.
Okay, what is e to the minus 0.3?
Alright, e to the minus 0.74.
Okay, multiply that by 100, you get 74, right?
Yes.
And so you already got 74 times negative 200 would be negative 158. No, 148. Right?
Times negative 200.
Yeah.
Yeah, it's 148.
Negative 148.
Well, times negative 200, I get negative 148.16. It's like pretty much saying 14,816.
Wait.
Yeah, I don't know.
Let me see. You're in it so bad I'm not understanding. Oh, no, okay, right. Wait.
Yeah, because the decimal point right here.
Okay, wait. You did the same answer as before. E to the minus 0.3. That's times 200.
Okay. So let's go e to the minus 0.3.
Right?
All right.
Times negative 200.
Times negative 200.
Yeah.
Okay, there we go.
Negative 148. Yeah. Okay. Approximately. Okay? Now, that's the vector. Okay? Pretty decent sized vector there. It's asking for the, find the directional derivative of f at p in the direction of the unit vector u, making an angle of theta equal pi force with the gradient. Okay? So what we have to do now, okay, if you go back to this, you see you need the magnitude of that.
Yeah.
Okay, so we got that. Okay, this was the gradient vector of f at minus 1, minus 1. Okay, that's what that was. The magnitude of that, of gradient of f at minus 1, minus 1, would be the square root of 74 squared plus a negative 148 squared. Okay? Now, you can do that. You got your calculator, you can do it. It's not impossible.
That's 74 squared, right?
74 squared plus, and you don't need to put the minus in there because when you square it, it's going to be positive anyway. 148 squared. And then take the square root of that. That answer.
That's 165.47.
Okay. 155. We'll just
165.
165.
Yeah.
I thought it should be bigger than that. Okay, 165.
0.47.
Okay, I'll just leave 165. That'll be close enough, I think.
All right.
Yeah, they did 165.5. Okay. Okay. Just to keep what the book has. Okay. Now, if that's the magnitude of that, then all that we do with that is now multiply it by the cosine of pi fourths, which is root 2 over 2. Multiply that by root 2 over 2.
I get 117. That's it.
About 117, that's what they got to. Yeah. Okay. About 117. Now, says recall the x and y are measured in units of 100 meters. Therefore, the interpretation is the following. If you stand on the mountain at a point lying above minus 1, minus 1, and begin climbing so your horizontal displacement is in the direction of you, then your altitude increases at a rate of 117 meters for every 100 meters that you climb. So you have to go back and put that as, not as 1, but 100. So that's saying you're going up a pretty steep slope. If you had gone up this way, the steepest slope, you'd be going up 165 meters for every 100 meters you went. So that's a really steep slope. This way you're better than, you're steeper than a 45, but you're not as steep as the other would be. The gradient would be the maximum slope. This would be the minimum. So that's what they're talking about here. Or a displacement of 1.17 meters in height for every one meter you went horizontally. For each horizontal displacement. Okay. Now, okay. And this, by the way, this is, I don't know, that doesn't quite look right. Who said you were at 2,500 to begin with? I don't know. I don't think it's at 2,500, but that's where they put the point. And the maximum increase would be to go in this direction. You're doing 45 degrees to that, so you're going up this way. You're still going up a pretty good steep slope here, but it's not as steep as if you were going up that way. All right. Let's see what's next. There is a little blurb here. They say conceptual insight, the directional derivative is related to the angle of inclination, psi. They say psi and psi. I don't know why they would say that. I've always heard it psi or c, okay? And it says the tangent of c would be your directional derivative in the direction of u. So, all right, enough of that. This is example 11, I think. So it's the very thing we were talking about, the angle of inclination. You're standing on the side of a mountain in the shape z is equal to f of xy. Now that's all they say, z is equal to f of xy. There is your shape of the mountain. No numbers in this one, just that. At a point Q, which is AB, f of AB. So you come out XA over YB and then up to f of AB. So it's somewhere up there, okay? Where your gradient function at AB is 0.2, I'm sorry, I can't read, 0.4, 0.02. So 0.4 in the x component and 0.02 in the y component, okay? Find the angle of inclination in a direction making an angle, goodness gracious, angle of inclination in the direction making an angle of theta equal pi thirds with the gradient. Okay. Boy, what a weird way to put the problem together. And I don't think we're going to have the time to finish it. So let's just pick up with that next time. Example 11. Okay? We almost finished 14.5. Homework exercises here, do 1 or 3 or both, 5 or 7 or both, any of the odds 9 through 19, any of the odds 21 to 29, either 31 or 33 or both, I think you can do 35 and or 37 and or 39. So let me go back and say any of the odds 35 through, I think it's 35 where we started, wasn't it? Yeah, 35. No, do 35. That's what stands alone. Do 35, and then you can try some of the odds 37 to 43. Okay. And then we'll pick up and go from there. All right. I couldn't find where my mark was on the page. There it is. Because we do have to stop now because we've got differential equations coming next, right?